Hello to everyone. I am Shashi Shekhar Singh, pursuing my PhD from Motilal Nehru National Institute of Technology, Allahabad. My presentation topic is effect of crack section properties on the seismic performance of RC and FRC building. Now, this is the outline of the presentation. Started with introduction, then why fibers and post concrete has been considered in this study, then objective of the study, then what the methodology has been considered, and building description, material and design consideration. On the basis of that, result and discussion, then after conclusion of the study, then future study, and at the last, references. Now I started with the introduction. In the real world, crack-free RC building is practically not possible. So if it is not possible, then cracking in RC building increase earthquake risk by reducing strain, ductility, and energy dissipation. And if we will ignore the cracking, it means ignore the stiffness modifier. The meaning of stiffness modifier is moment of inertia. What we are considering for the analysis of crack section in case of this study from IS 1893 2016 for column 70% I gross and 35% I gross of in case of beam has been considered. So it means ignoring the stiffness will lead to overestimation of seismic resistance in design. Also, Indian Seismic Code IS 1893 lack clear provision for modeling FRC and also incorporating nonlinear behavior. And what the FRC can do? So FRC is usually doing the post cracking strand, ductility, and the energy dissipation capacity. In next slide, we will see in more detail why FRC has been considered. From this above, we had find the research gap. No Indian guideline currently integrate FRC behavior. This study aims to compare the seismic performance of uncracked normal concrete building, cracked normal concrete building, and FRC, cracked FRC building. And also the second aim is the use pushover analysis with stiffness modifier from Indian code. The final goal is advocate for the codal upgrade by showcasing FRC capacity to enhance seismic performance in reinforced concrete building. Then why FRC? What is the meaning of FRC? First, we have to try to understand the meaning of FRC is the fiber and coarse concrete. It means the concrete matrix, the fiber has been incorporated, and because of that, at the material level, improve stress resistance curve, and after that material level, the disperse the stress concentration throughout the member, and because of that, in global context, it can improve the base shear capacity, energy dissipation, and global ductility and it will ensure the building safety and functionality. Now coming to the next slide. I had formulated the objective of this study. The first objective is to investigate how the cracking affect the seismic performance of RC building, to assess whether the FRC can compensate for seismic performance losses due to the cracking, to compare seismic performance like ductility, base shear, energy dissipation of uncracked normal concrete building, cracked normal concrete building, and cracked FRC building. To apply stiffness modifier from Indian code in modeling and also use nonlinear pushover analysis for seismic capacity evaluation, or to recommend update in the Indian seismic design code for FRC inclusion based on finding. Now, this methodology has been considered starting from this point. The first step is the improvement of concrete material with fiber, like that here we can say in the normal concrete and 0.5% cream steel fiber material. The stress resistance curve has been improved. Also, the second confinement of beam and column. I am doing in this study with the Menderatum 1998, and the improvement of material has been done with the Natarajan et al. 1999. Then after assignment of stiffness modifier from Indian Code IS 1893 2016, after that the linear analysis and design. If in and linear analysis and design fail, then again go to the first and second step. And if it will pass, then the moment curvature illustration of beam section. And after that, hinge definition and assigned to the beam M3 plastic hinge, and column for column PM to M3 fiber hinge. The fiber hinge we can see here the categorize the cross section into the core and the cover, and the small element and the reinforcement also categorized in the fiber and assigned to the column. And in case of beam, moment curvature data has been assigned to the beam. After that, to some more analysis, and we will get the capacity curve for comparative investigation. Finally, we are getting energy dissipation, global ductility, and base shear. This is the complete flow chart. This is the building description, material and design consideration. G+2 building has been taken. The beam and column details has been given. Also the design details, building details and material details has been given in tabular form. And also the different types of building description and the moment of inertia what we had taken in this study. The result obtained in this study in the tabular form, we will see the building seismic performance and the X direction, the types of building NCUC, NCC, and FRCC. The global ductility of NCUC is 3.9, and NCC is 2.3, and FRCC is 4.5. So from a normal concrete and crack building, it has been improved from 3.9 to 4.5, or it is compensating also the cracked section behavior. Also in case of base here, it is equivalent, nearly equal 1074 in uncracked normal concrete building and 1075 in cracked FRC building. So FRC has, and also the posterior dissipation capacity, it has been 3.8 times improved with respect to the NCUC. So here we can say like that ki FRC is enhancing the compensating the cracking due to the cracking in the normal concrete building by FRC incorporation of FRC in the construction. Now the conclusion, this study evaluates the impact of crack section property on the seismic performance of RC building and demonstrate the advantage offered by FRC in enhancing building performance. Here the first is the crack section property significantly reduce the seismic performance of RC building by lowering ductility, energy dissipation and base shear capacity. The incorporation of 0.5% trimmed steel fiber into the concrete improve mechanical properties and enhance structural integrity under seismic load. The FRC building outperformed a cracked normal concrete building and match or exceed the performance of uncracked normal concrete building in key metrics compared to normal concrete uncracked building. FRC building in FRC building ductility increased by 15%, base shear capacity remained nearly equivalent, energy dissipation increased by approximately 3.8 times. Also, the next conclusion, if possible, anything confirmed FRC can maintain seismic performance despite crack section. These results validate the use of FRC for seismic retrofit and as well as the new construction in in earthquake prone area. The study strongly recommend updating Indian seismic design code to incorporate FRC specific design provision. The use of cream steel fiber in RC structure promote PVD performance based design and contribute to safer, more resilient infrastructure in seismic zone. These insights paved the way for incorporating FRC into the seismic design, like Indian Seismic Design Code, ultimately advancing the development of safer, more resilient infrastructure in earthquake-prone region. These are the future study. You can see to enhance the practical applicability of FRC in structural engineering. Future studies should consider revised Indian seismic design code to include cracked section modeling of for FRC. Mandate stiffness modifier for both the normal concrete and FRC design checks. Assign higher response factor, which is responsible for the FRC structure reflecting their improved ductility and energy dissipation capacity. Develop standardized modeling guidelines for FRC in a structural and also school like SAP 2000, especially in the non-linear scenarios. Encourage the use of fiber in both new construction and seismic retrofit of existing RC building. Promote experimental validation of FRC building. FRC-based design to build the confidence in their seismic reliability across varying building height and geometry. Educate design engineer and code authority about the performance benefit of FRC to accelerate practical adoption. These recommendations will contribute to a more comprehensive understanding of FRC potential in enhancing structural resilience and sustainability. These are the references. Thank you. Question and suggestion are welcome.